Hi folks, Buckley here. This is workshop number 19 in MEEG104. Today we're going to talk about data organization and intermediate Microsoft Excel functionality. Before we get going though, a couple reminders. Formative assignments. Number 18 is due 2 p.m. Monday, April 27th. 19, which will be associated with today's workshop, 2 p.m. Wednesday, April 29th. There was no required reading from last time. You should be working on your summative assignments. Great questions that are being posed to the discussion board. I'm trying to answer those as those come in. Please don't email me with your questions. Go ahead and post them to the discussion board. So summative number 2 draft is due at the end of this week, or actually Wednesday, April 29th. Okay, so keep working on those. All right, live help. There's optional discussion sections with me on Mondays and Wednesdays, 3 to 3:30. Looking forward to talking to you all. All right, before we get going on the core of today's workshop, I do want to correct something. So I made a mistake, and when I make a mistake, I like to fix it just so there's no misconceptions. This was an honest mistake, and actually people had questioned me on this, and I was adamant about it being a certain way, and I was wrong. So let me fix it. Okay, so for summative number 2, I misspoke about rubber band circumference not affecting stiffness. It actually does affect stiffness, okay? And we'll work with this a little bit more in our videos as well, so if it doesn't sink in right away, I'll make sure to reiterate it on the Microsoft Excel tutorials as well. But stiffness does affect, or I'm sorry, length of the rubber band or circumference of the rubber band does affect its stiffness as follows. Okay, so we've got a rubber band. If I pull on it, F equals Ks, force applied, is equal to the spring constant times the stretch, okay? That spring constant has something embedded in it, okay? So if I look at the spring constant from a material perspective, K, okay, is actually equal to E, which is the Young's modulus, or the elastic modulus of the rubber band material, times the cross-sectional area of the rubber band, divided by the length of the rubber band. And the length that we're interested in is actually this length here, side to side, okay? And the area would actually be double because we got 2 sides to it, but that's a small detail. I was mistaken because I thought that because E was constant, K would be constant, but that is not the case. Okay, you'll see that the term L, that total length, which is going to vary depending on the circumference, does factor into K, or the stiffness. Okay, so constants here in this expression, we're dealing with the same rubber band manufacturer who is using the same material to produce those 3 sizes of rubber bands, small, medium, and large. Okay, so E for rubber used in rubber bands is about a 1/100th of a gigapascal, or 10 megapascals. Okay, the cross-sectional area of the rubber band is going to be equal to its 3 millimeter width times its 1.5 millimeter thickness, which is 4.5 millimeters squared. Those are constant for the small, medium, and large sizes. Okay, so E and A will be the same for those rubber bands. L, however, will vary with the circumference. Okay, so L is going to vary with the size. Okay, so there is enough information now to compute K for the different size rubber bands. Okay, so I did update the problem statement ever so slightly. I'm telling you that the box of sample rubber bands that you were sent to test, the quality control team was sent to test, were size medium. Okay, those were medium-sized rubber bands. All right, so let's go back to that expression, K is equal to EA over L. I could write this for my medium-sized rubber bands, which I know what K is experimentally, I've determined it, okay, is equal to EA over LM, the length of the medium-sized rubber band. Similarly, I could write the stiffness of the large rubber band is equal to EA over length of the large rubber band, and stiffness of the small is equal to EA over length of the small rubber band. Km, again, I have determined experimentally from those 30 samples that were provided. So that is known data, that is known, okay? I also know that EA is constant across all 3 groups. So I could do some simple shifting here, and I could say EA is equal to Km times LM, because LM is also known, right? It's going to be some function of the circumference of the medium rubber band. And then I could replace that in these expressions for Ks and Kl. So everywhere I see EA, I could just write Km, Lm. Okay, so that would give me an expression, something like Kl is equal to Lm Km divided by LL. So knowing km, which I know experimentally, and knowing the ratio of the rubber band lengths, which is just going to be the same as the ratio of the circumference, okay, I can determine KL. And I could do the same thing for KS, right? So KS would be equal to LM KM divided by LS for the length of the small. And in place of length here, you can just replace the circumference because we're going to assume that those rubber bands are deforming in the same way. They're doubled up on each other in the same way, so we would just use circumference there. Okay, sorry about that, guys. I apologize, but I'd rather fix it now because some of these concepts are going to come up in a year in MEEG104, and I want to make sure that this is correct. Okay, so I will tell you if you have already worked your calculations with K being constant, I won't fault you on that in the draft. I will expect you to update that in the final, but I won't fault you for it in the draft. Okay, that was on me. All right, with that update behind us, I'd like to talk about our learning objectives for today. They are twofold. The first is we're going to apply formatting and design guidelines for spreadsheets and data sets. We're going to focus on what you need to organize your spreadsheets so that they are readable by others. And our second learning objective is to explore the advanced functionality of Microsoft Excel. We're going to do 2 videos on Microsoft Excel advanced functionality. One is going to be super relevant to formative assignment number 19, and the other one is just a bonus track for advanced Microsoft Excel. Microsoft Excel is actually quite fun once you get to using it. Okay, we're going to start with a self-reflection though. So I want you to think about how you organized your data for summative number 1. So think back to summative number 1. How did you organize the data that was going into that? You had to compute the throughput on a 3D printer, okay, and then you had to come up with a production schedule. There were some calculations involved. How did you deal with those? Did you deal with them in a spreadsheet, in a Microsoft Word document? Were they handwritten? What did you do? Reread, okay, I'd like you to put me on pause and actually open up and look at your data, how you actually did your calculations. Can you understand your process when you look at it? Third question is, could somebody else who is loosely familiar with the project, maybe they have read the problem statement, could they understand your process? Could they understand what's going on in your data files? And then the last point is, what elements made your data understandable or not understandable? If you're thinking about not understandable, what else could you have added to make it easy to interpret? Okay, put me on pause, open up your data for summative number 1 and take a look. There's my example from my summative number 1 on the right. Okay, if I were to guess, when you just open up the summative number 1 data file again, you're going to see something like this, okay? So I would guess that a chunk of you used Microsoft Excel. I saw some people in their write-ups also did hand calculations. I didn't force you to use Excel, so that's totally fine. But let's assume for a second that you used Excel to do those calculations or to organize your data in some way, as I did. Okay, so let's do with a little critique of this, right? So one thing that helped in understanding this data, okay, so I did a decent job in allowing a user or myself looking back at my work to understand what was going on. I do have variable descriptors, right? So I don't just have numbers on a page with no description next to them. I have some descriptors, so COG, which is our abbreviation for cost of goods without the tower topper, 415. Okay, I'm assuming that's probably because it says cost, maybe that's in units of dollars, okay? Print times single 1.42, okay? Number of printers 8. So I've got things that kind of make sense. So I do have variable descriptors. I do also have a worksheet title. So you could tell that on this page here, I'm dealing specifically with 3D printing. Okay, so these were some calculations that were relevant to 3D printing. Things that I could clarify though, okay, so on this spreadsheet, there's really you don't know author, date, and version. Okay, so who did this work? What sources were you pulling from to come up with these numbers? Also units, right? So again, I'm assuming this is dollars here. Print times single, I'm assuming that's going to be hours, maybe. Okay, and then the other thing that's not totally apparent is which is essential input and which is output. Where did I get these values? What am I looking for as my final result? A lot of times we assume that the last line in a little section here is maybe what's important, but that's not really highlighted. Okay, so I'm showing you my original spreadsheet. to show you that there's improvements that could be made here that could make this data file more readable to somebody else who's picking up my work. Or if somebody has questions about my work and I have to go back to it after a number of weeks, months, years, I could look and see what I did, right? So the more information that you put into your spreadsheet or your data sheets, the better it is, the easier it is to interpret, okay? And that's really what we're talking about in this lecture, is how can we make data sheets that are going to be easy to interpret by ourselves if we go back on that work, or by other people if they're picking up where we left off. Okay, one good point about what I did was this is fairly concise and organized. Okay, so I don't have numbers scattered all over a big page. It's kind of nice and tight up in the left-hand corner, which would be the first part that would display on my spreadsheet. So I did decent with variable descriptors and concise, well organized. I also have a worksheet title. So just so we know, this entire document, okay, the entire file is called a workbook in Microsoft Excel. These are individual worksheets, okay, and you can have different ones as you go through. Okay, but there are some areas of improvement, again, that I could clarify. All right, I want to take a step back for a sec and talk about this concept of spreadsheet. The concept of spreadsheet is an old concept, okay? We are not the first, Microsoft was not the first to come up with this, okay? It's been around for a long time. Old spreadsheets were simply just empty books, okay, that had lines in specific places. My father, who ran a business for a very long time, my mother and my father kept, for some time of that, back in the 70s and 80s, they kept a physical spreadsheet that looked something like this. Okay, and that was where they did their books, right? That's where they made payroll and those sorts of things. So a lot of times spreadsheets really originated from the business world, although scientists picked it up and found it to be useful as well. These sheets go on and on and on. It's just a blank book that would look like this, and some of them allow you to flip back and forth. So you would have your row labels over in this area, and you could flip back or fold the pages so that you could see across very long column widths, okay? So a ye olden spreadsheet, also called a ledger, has been around for a long time. So it allows for organization of complex data into rows and columns that are appropriate for calculations. Okay, and you can see here probably these are totals, all right? So you could add down a column. That's very easy to do to get a total, right? It accommodates very large data sets, so years and years of business books, okay, or rows and rows of data. Modern spreadsheet software, for which Microsoft Excel is far and away the most common. There are others. There's a version called Numbers that nobody uses, okay, but most people use Microsoft Excel, and if you are to get proficient in one spreadsheet software, I would highly recommend it's Microsoft Excel. Modern spreadsheet software allows for a couple things. The first is it has fairly advanced mathematical functionalities. So all the functions that you have on an advanced calculator and then more, you would have in that spreadsheet. Sine, cosine, tangent, exponential, pi. Okay, all of those math functions are inbuilt, which is super important for scientific calculation. It also allows for easy sorting and filtering of data, and also has graphing capabilities. We've worked pretty extensively with the graphing capabilities in Microsoft Excel in prior workshops, so I won't be highlighting it here. Your two videos and your formative will deal with the mathematical functions and the sorting, filtering of data in Microsoft Excel, which are two functionalities that we haven't explored in huge detail. Okay, so the origins of a spreadsheet are a bit older, but modern spreadsheets can do that and a whole lot more. So if you are using spreadsheets as a form of data collection, which most of us are in today's day and age as engineers, you want to design and format your spreadsheets to allow others to interpret the contents. There are 4 items that you should consider when you do this. The first is an information section somewhere on your spreadsheet. Okay, some people prefer to have it as a cover sheet, so a separate sheet that basically lists all of the relevant information about the entire document. Other people prefer to embed it within a single sheet, but there should be some general information that tells the reader about this document. Also helpful is titling. Okay, so making sure that you're titling individual sheets within the workbook. Again, sheets are individual pages. The workbook is the entire file or the collection of sheets. Second thing you want to think about is column and row layout and labeling. Okay, we'll get into this in a second, but how are you going to lay your data out so it's easy to read? Third is optional. Okay, so sometimes you do need to include notes for clarification. Sometimes data sets are so simple that you don't need notes, but a lot of times with more complex problems, notes are very helpful for somebody who's coming along behind you and reading. The fourth thing would be using multiple spreadsheets, okay? Using multi-sheet workbooks or multi-sheet spreadsheets when your data, you have various calculations that are related to a single project. So you'd like to keep all your calculations within the same file, but they're kind of unrelated to each other and really belong on separate document pages or sheets. Okay, so let's talk about that as well. All right, going through these one by one, let's start with element number one, including an information section and titling worksheets appropriately. Okay, so here would be my workbook page, my worksheet for 3D printing, redone in a better format, addressing all of those issues that I found before. The first thing that I should do is really include an information section. So typical on a project would be to have a subject, an author, dates, sources of information, and then notes. Okay, so if you're looking for a standard header, it's not all that different from part of it looks like a memo, right, on a regular document. But having that information basically is kind of like when you're coding, okay, you know how you're supposed to include a standard info section. You can think of it the same way with Microsoft Excel sheets. So here, the subject, which is the subject of the sheet, is back calculations for 3D printer throughput and gross margin. I'm the author. Okay, original date was February 2020, and I updated it in March. The sources are the 3D printer cost time estimator, right? So that was what I used to do a lot of these calculations. And notes, okay, so the notes are pretty important here. It says green cells are essential input and orange cells are essential output. Okay, more on that in a sec. All right, the other thing that happens here is that I want to make sure if I have multiple sheets in this workbook that I'm labeling the sheet itself so you know what it says. We don't want it to be sheet 1, sheet 2, sheet 3. Those are the default settings. Please take a little time and give your worksheet a meaningful title. Okay, those can be very helpful for somebody else navigating your work. Element number 2 is laying out the data in rows and columns to facilitate readability and data analysis. Okay, so we'll talk about readability in this document because this is really a long-form calculation that we're performing in Microsoft Excel. We'll talk about how to lay things out for data analysis a little bit later in those YouTube videos on functionality. Okay, but for right now, we're basically using Excel as an advanced calculator. So first thing is I have essentially what's a 2-column layout. So I have a parameter, which is, and I'm providing the name, print time, number of units per day, okay, parameter down here, cost of goods, okay, and then I've got a value. And notice that I'm specifying the units, okay, so anywhere that I needed clarification on what the units are, this is in hours, this is in dollars, okay, and then this layout is kind of condensed and to the left. So I want to not have these values free floating all over the page, right? Lay it out as if you were neatly writing or doing a computation by hand, right? You don't scatter your notes all over the page. You want to do the same thing in Microsoft Excel. That's what we mean about readability. Element number 3, consider adding notes for clarification. Again, there are notes that apply up in the header section for the entire sheet. Okay, these say green cells are essential input, orange cells are essential output. Okay, and then there are notes that can be associated with particular lines or rows or columns in your spreadsheet here. Okay, so these are little notes to myself about where I got this information. Okay, and then also notice that I've color coded, so if somebody wants to use this as a calculator, let's say I change one of these values and these all update as live links, we'll get into live links in the YouTube video, I could see exactly where I should change my inputs, those would be the greens, and exactly what output values I would need. Things that aren't shaded are actually calculated values that are interim values that aren't really needed to be highlighted, okay? So those are like back calculations. All right, element number 4, also optional. If you're doing a lot of calculations, folks, okay, so you have a lot of different calculations that you're performing or a lot of different analyses that you're performing for the same project. Maybe they involve slightly different data sets. So for example, in your Summative 2, you have one data set that it's the raw data from testing of those rubber bands, right? Tension testing of the rubber bands. That would be one data set. Maybe you have several sheets that are devoted to that data set, and then you'd have several sheets that would be devoted to the calculations that would occur after you've computed your K or your stiffness values, right? So those belong on multiple sheets. Looking back to my example for Summative number 1, okay, I have one sheet called 3D printing. That's the calculations relevant to 3D printing. Okay, so printer throughput and printer gross margin. Okay, that's the worksheet I've been showing. Then I've got another worksheet called production schedule that are calculations for the production schedule. And notice I have a different header on this. I've updated it. Okay, my sources are different. Okay, then let's say I want to plot the production schedule. Well, I would put that plot, okay, these are figure 2 and figure 3, are graphs of the production schedule. I've got two different ones, okay, but they're pulling from this data sheet. Then the last thing to note is that let's say that you want to format a table to include in a document. We've already worked with Microsoft Excel as a way to format tables. Okay, a lot of times you don't want to do the formatting on the same data that you are doing your calculations. You would actually like to copy these as values and then reformat those as a separate sheet. So here would be the nice, neatly formatted tables. This one I'm including actually. First, my summative one I included in the main text, and then this table was presented in an appendix, but it's much, much cleaner than the version before. So this is the same data, just formatted neatly for it to be shown in an appendix. Okay, these are all on different sheets, folks, within the same workbook. Okay, that's another way to keep my data organized. I'm not putting it all into one spreadsheet, and that spreadsheet is super huge. For the most part, unless your data set is very large, unless your data set contains a lot of columns or a lot of rows in and of itself, you don't want to include a lot of different components, graphs, multiple versions of the same table, multiple versions of different calculations on the same worksheet. You'd like to spread those out onto different sheets. Okay, with that, guys, we're going to do our class participation activity. So the class participation activity is going to involve everybody critiquing a spreadsheet from a senior design project that contains experimental data for a provided engineering design report case study. So that case study is one that I use as an example in class a lot. It's the senior design team tree hugger. The experiment that they're conducting is basically they are varying various parameters. This is their actual product here, is this little webbing that goes over a tree base to keep it to grow steady, okay, grow vertically. And they're varying different parameters associated with this design, the number of different loops, the depth of the stakes, whether or not it has a slit in the front of it, okay? So they're changing this design. They have different tests that they're running, and the main test outcome is whether or not this is stable. So the way that they're determining stability is they've got a fake tree that they are pulling over, they're ratcheting it over, and they're measuring the force it takes to basically cause that fake tree to go at an angle. Okay, so the less force that it takes, the less stable their product is in that particular configuration. They're calling it the overturning moment test. Okay, so you want to read a little bit in this class participation activity to get that background. So read the design validation section of the main report, pages 14 through 16, the overturning moment test, to learn about this setup. And then you should also read Appendix G, pages 30 to 32. So please read 4 pages of the report to get the necessary background. Then look at the spreadsheet that I gave you. That spreadsheet contains their raw data. How well did these authors apply the organizational elements that we just covered for spreadsheets? I want you to focus on number 1, was there information titling? Okay. Did they appropriately lay out columns and rows? Were they labeled? Okay. Were there notes for clarification when needed? Did they spread their data out over multiple spreadsheets? Okay, those are the 4 questions I want you to answer. And then I want a general statement, which is the spreadsheet understandable to you as somebody who's now only cursorily or briefly familiar with the project, okay? So think about those questions and respond in Canvas. Put me on pause, please, as you do it. This will be about 15 minutes. Okay, I'd like to highlight a couple things from class participation activity. This is not the full range of issues with this particular data set, but it's some of them that I'd like to at least acknowledge. Okay, so here's a screenshot of the spreadsheet, 1 page of it. This is a sheet labeled control. Okay, so first thing to notice is that there's no real header on this sheet. Okay, so it would be helpful to have that header there. And then they did do a decent job with sheet titling, so they did title it control, so I could assume this was the control group, but this information up in the header really doesn't add anything to the sheet titling. The next issue that I have is that the layout of the data isn't condensed. Okay, so there's no reason that mean, standard deviation, max couldn't sit over here. Okay, it's kind of floating out in space, taking up more real estate. Maybe there's a way that this could have been laid out so that you have trial number, force, angle. Okay, and this is all in, so trial number would be one column, force, angle, and you'd have trial 1 going down to 3. We'll see in some of the videos how that makes it helpful in terms of data analysis to organize your data that way rather than have these tiny little tables spread out everywhere. The last item is there is sort of a free-floating cell out here. This is the mean of what? I'm assuming they took the mean of the means, but what is this value tied to? That isn't really a descriptor. Also, it's highlighted, but there's no context for the highlight. Okay, so some issues with readability on this, although, you know, I can generally follow what they're talking about. There was a sheet in here called analysis that was not very good, and I'd like to highlight it. So this is an example of putting too much information on one sheet, so much so, in fact, that sometimes you're covering up essential information. So we're the first ones to come in and look at this sheet. I've got tables and graphs on the same sheet. These would be better as sheets in them themselves, and that would also address some of the formatting issues with these looking really tight, okay? The other thing is there is a lot of space. There's a lot of dead space on here. Again, probably because they wanted to include those tables there, but these really do belong on a separate sheet, okay? All right, so those are some edits from my critique of this work, okay? Hopefully you found some other issues with it as well. All right, I'm going to change gears a little bit now, and I'd like to talk about, in concept, Microsoft Excel and its capabilities. There are going to be 2 YouTube videos that go along with this, one that's going to be essential for formative number 19, and one that is more of a bonus track. Microsoft Excel, thus far, we've been using it to graph things, maybe do some really simple calculations, but we really haven't used its full capability. Microsoft Excel is more than just a spreadsheet, okay? It's a visually driven computing language when you think of it. And the deeper you get into Microsoft Excel, okay, actually the more you can use it as a computational platform. It doesn't have all of the functionality of MATLAB and Python, okay, or C++, but it does have a good deal of functionality. It's actually quite surprising. And the fact that it's visual and the fact that you can work with large data sets right in front of you, you don't have to import the file and then you're running code that might crash, okay, makes it highly beneficial. So I love working in Microsoft Excel. So what can Microsoft Excel do? Well, it can, you can do mathematical expressions, okay? So again, all the capability that you have with an advanced graphing calculator or MATLAB or Python, sine, cosine, tangent, exponentials, pi, okay? All of that is contained within Microsoft Excel. You can apply logic statements in Excel, okay? Again, it doesn't have all the functionality of a programming language where you can do do loops and that kind of stuff, but you can do if statements. You can test values versus each other, okay? You can also do graphing, so MATLAB and Python also can do graphing. Excel does graphing super easy, and you can play with the formatting much easier than you can in MATLAB or Python. MATLAB and Python do have some data sorting capabilities, but Excel, this is where Excel really shines, okay? Because Excel was primarily designed as a business platform, there is a lot of sorting capabilities and database functionality that is inbuilt, and we'll get into that as well. But what I'd like to talk about right now in preparation for your formative number 19 is really the mathematical expressions that are going to be useful in Microsoft Excel. Okay, so our first video is going to focus on mathematical expressions, and the second one is going to do data sorting and filtering, data sorting and filtering and logic statements. We've really done all of the graphing functionality I need you to know. Okay, but let's talk about in preparation for the mathematical expressions. Okay, I want to talk a little bit about this concept of drag, okay, because that involves a lot of computation. Okay, so drag is something that we haven't considered yet in our summative number 2, and I told you that it could be optional, so you don't have to include this, but it definitely is a factor from an engineering perspective in designing your rubber band shooter. What you see in front of you is actually a trajectory of a bullet fired horizontally. Bullets actually are designed to have minimal drag. Okay, as you can see here, the values between no drag and then with drag are very, very close. This is a graph from Mythbusters. Our rubber band is going to experience high drag. Okay, so these lines are going to deviate, and the drag is actually going to cause it to have the rubber band to shoot far less of a distance than without the drag. Okay, so what's going on? Let's look at this from a physics perspective. We've got our rubber band and it is flying through space. Okay, this is the vertical position and this is the horizontal position. So it's somewhere sort of mid-span. It's come off the gun and it's flying, or the shooter, and it's flying through space. So first thing that's happening is gravity is pulling that rubber band downward, right? So gravity is acting on the rubber band, which is why it is falling to the ground. But that is the only thing that we have considered prior to this point. What is happening in actuality is that there is also a drag force, FD, that is acting on the rubber band tangent to its velocity. Okay, so it's acting in the direction of the velocity. So here it would be pointing back up along this curve. So it would be acting upwards and to the left, okay? That drag force is computed experimentally, so there's an equation for it. Okay, so that force of drag is equal to 1/2 c rho AV squared. C is called a drag constant, drag coefficient. Rho is actually the density of air. A is the effective drag area. So C and A are actually tied into each other. And sometimes you'll see C denoted as C sub D, okay, drag coefficient. V is the velocity. Okay, so V is the velocity of that rubber band. What makes this tricky, folks, is that velocity is changing. Okay, every instant in time you have a different velocity on that rubber band, right? And that velocity is tied in with its position in X and Y. Okay, so you've got a mathematical expression here that ties in at every instant in time. You've got velocity that is changing, that is affecting the force, which is in turn affecting the acceleration acting on the object, which in turn affects velocity. So it's this iterative loop. That's what makes this computation, or this solution, very complicated. That's actually why the best way to solve for the path with drag is to do it using a computer. Okay, so it's very hard to get a closed form or writing long form out all of the math solution to this problem. It's a very complex differential equation. You guys, some of you may have been exposed to differential equations. If not, you'll get it in Math 351 and Math 352, which are coming up in the curriculum. Okay, so I'd like you guys now to put me on pause and to go to this website. This website is an online simulator comparing projectile motion with and without drag. Okay, so go ahead. This is the URL that I did on Bitly. Okay, and then this guy is a QR code. Take you to the same place. You should see a screen like this. And then what I want you to do is actually play with these sliders. So what you're seeing here is the blue line is the trajectory without drag, and the red line is the trajectory with drag. Okay, and you can play around. Put me on pause. Have fun with this simulator for a sec. All right, I want to highlight that what's running in the background on this simulator is the solution to this problem here, okay? So it's basically computing the velocity every second, updating the drag force, and then working out what the acceleration of this object would be, deriving the velocity from that, deriving the position from that, okay? So it's an iterative process to come up with these solutions. All right, some things that you may have noticed playing with this. First, you should try to set the constants here, okay? So this particular simulator, they left everything open. We are on Earth, okay? So you should use 9.81 meters per second squared for the gravitational constant, okay? Or acceleration due to gravity. Rho air is the density of air, is also a constant. It's 1.225 kilograms per cubic meter, okay? So try to set that there. And then the other things are things that are going to, and if we're thinking about the situation for summative number 2, okay, we've got some experimental parameters that we want to deal with. The launch height, okay, is a child who is shooting the rubber band shooter horizontally at whatever approximately their shoulder height is. The launch angle should be about 0 degrees. You'll notice that this won't go down to 0 perfectly at 0. That is a function actually of the differential equations that are being solved. It'll actually crash the system if it's at 0. So this uses, I think, 0.1 as the minimum launch angle. But that's close enough. If you think about it, the kid is probably not directly at 0 on the dot. They're a little off from that. So 1 or 2 degrees or 0.1 degrees would be just fine. Okay, design parameters that you need to consider when you're selecting or when you're modifying your shooter design and or selecting the appropriate rubber band are the mass of the rubber band, the effective surface area of that rubber band flying through space, the launch velocity, right, which is going to be a factor of your rubber band stiffness, the stretch, and also the mass of the rubber band, and then the drag coefficient. Okay, so I want to focus in on a second on what are reasonable values for surface area and drag coefficient. Okay, these are things that are actually sometimes people can compute these in closed form, so they can solve for the solution in closed form. Other times it's done computationally. This gets into fluid dynamics, okay? So you guys will deal with drag coefficients and Reynolds numbers in your junior year fluid dynamics classes. You have 2 of them, but a little preview here and how to use it. Okay, so basically this is the drag CD, and then the reference length is also an important variable. It basically tells us what area is getting contacted in profile as this object is flying through space. Okay, so a sphere has a certain CD, which is 3 pi, hemisphere 8.7, normal disk, okay, parallel disk, normal rod, parallel rod. Okay, so let's think about this guy flying through space. A rubber band flying through space would experience air coming up against it, right? Okay, in this direction, in this shape of the profile. So CD would be, in this case, it's more of a parallel disk. 16 divided by 3 is 5.33. Okay, the effective area would be the circumference divided by 2, okay, which would give me the length, times the width. So the width, the depth into the page, which would be about 0.003 square meters. Okay, in this profile, I have the same A, okay, the same A, but my CD in this instance is going to be 8 because my disk is oriented upright. Okay, now these aren't perfect. Okay, I would say that I'm going to leave in your calculation CD as a variable is something that you can interpret. I would say on the low end, CD is probably around 2, and on the high end, you're probably looking at that value of 8. Okay, and obviously that rubber band is going to change its orientation through space. So your assumption for the drag coefficient is going to be a big one. You're going to want to justify it in some way. Okay, maybe using tables like this or referring to this lecture, but you can figure out what that drag is. The higher the drag, the more of a difference you would see between your ideal no drag condition and your drag condition. What I'm providing to you guys is a computational solver in Python, okay, to determine shot distance with and without drag. This is what it looks like, okay. I didn't write this whole thing. I did pull some of this content from the same source that's actually used on this solver here, okay. Pulled it from the same source, but I did modify it. All right, and it takes some inputs. Okay, so your input values are actually going to be these guys here. So you're going to give this piece of code the stiffness, the stretch, the mass, the circumference, the rubber band width, the drag coefficient, and the initial height. Okay, so those 1, 2, 3, 4, 5, 6, 7 input parameters. Okay, and then this code will spit out the range, okay, or the shot distance with drag and the shot distance without drag. This value here should also match up with the calculations that you've already performed. Okay, so that bit of code is something I will also show you. I'll put that into one of the videos, okay, showing you how to work with this piece of code. Just as a reminder on Python, you are free to also modify this Python code as you feel fit. Formative assignment number 19 involves you using advanced mathematical functions and that Python solver for summative number 2. You're going to use the Python code to compute shot distance with drag. You're going to compute shot distance without drag in Microsoft Excel and cross-check your values with the Python code. You're also going to create live links in Microsoft Excel so that you can play with those parameters, stiffness, mass, stretch, okay, in helping you make your design. So basically, we're going to do some of the back calculations. I'm going to walk you through some of the back calculations in Microsoft Excel that'll be helpful for formative assignment number 19. Look for that video coming shortly. All right, that concludes today's lesson. Formative assignments, again, 18 is due 2 p.m. Monday the 27th, 19, 2 p.m. Wednesday, April 29th. Required reading is just watching these 2 YouTube videos. They will be coming, I promise. Okay, YouTube video number 1 is Advanced Math in Microsoft Excel. Also, I'll show you how to run that Python code. YouTube video number 2 is Logic Statements and Data Sorting in Microsoft Excel. Summative assignment number 2, the draft is due on the 29th. Please note that I did have requests for regrades on Summative number 1, and I am still working my way through them. I have not forgotten about you. Okay, it's coming. I should have those done for everybody this week. Okay, that's anybody who requested a regrade through Maddie. Okay. Live help, optional discussions with me on Mondays and Wednesdays, 3 to 3:30, and you can get that link via Zoom. All right, guys, thank you very much, and look for those YouTube videos.